Thanks. So good afternoon, everyone. I'm very excited to be here today to share with you a little bit of Google's perspective on quantum computing. So there's a couple goals for my talk today. First, I want to sort of just tell you where Google sees the field today and a little bit about where we think it's headed. But I also want to tell you a little bit about where Google sees itself in the ecosystem of quantum computing, and in particular, how we're working with customers currently and our vision for working with customers in the future. So to do that, I want to start by giving you a little bit of context about how Google sees its quantum program. And for that, you should really understand Google itself. So, of course, you all know that we're a search company. And you probably also know that the other substantial portion of our revenue comes from our ads product. So these two products, at least sort of in Google's self-perception, they're products that are powered by machine learning. So for us, machine learning is very sort of core to our existence, and anything that might disrupt machine learning is something that might disrupt Google. So one of the original motivations for why we got into quantum computing was that we do hope one day quantum computing will have an impact on machine learning, and that will be important for us. However, quite frankly, that's very speculative. We don't actually know what that will look like, or whether it will happen at all. Maybe a more down-to-earth goal is that we would like to be one of the premier providers of quantum computing hardware and provide that through a cloud service. But today, the reality is that quantum computers have somewhat marginal commercial value. In order to actually realize value out of quantum computing, we're going to have to develop better hardware, and we're going to have better algorithms. And both of those things are research goals that we're very committed to. But our business goal at the moment is very tied to this as well. In particular, our business goal is to actually discover applications of quantum computing. Because at this point, without better applications of quantum computing, it's not certain that there's really going to be a business at all. Okay, so let's talk a little bit about where quantum computers are today. I think you've heard from a number of speakers that we're in this so-called NISQ era, this era of noisy intermediate scale quantum computers, which means today we can run circuits on maybe 50 qubits, something like this, but there's a good amount of error in those circuits, which limits the size of circuits we can actually run. Nonetheless, you might have heard a couple months ago, we published this experiment where we revealed we had demonstrated quantum supremacy. So quantum supremacy is actually a relatively simple concept. It means we were able to implement an experiment on our quantum hardware, which solved a well-defined computational problem that you couldn't solve on a classical supercomputer. Now that problem was itself very contrived. It wasn't a useful problem, but it was at least a well-defined problem, and that was a milestone that we were sort of excited about. So on one hand, this means that we can generate very, very complex quantum states, and that really feels like it ought to be a resource and one that we should sort of figure out how to use. But the reality today is that the only application we know for certain we can actually realize with this quantum supremacy capable hardware is generating certifiable random numbers. And that's actually kind of a cool application. You'll hear more about it from Alan Ho later in the week. But it's not really the killer application we're looking for. It's probably not really going to pay the bills. And I should say also, tomorrow, the head of our hardware team, John Martinez, will be speaking about quantum supremacy, so you can hear more about that tomorrow. So what will these devices be useful for? So a number of people have spoke about quantum simulation today, and the idea that quantum computers are good at solving problems in quantum physics. And indeed, we do think it's highly likely that even a NISQ device will be useful for some sort of simulation of physics. But the question is sort of how commercially relevant is that going to be? So I like to think of a spectrum. And on one side of the spectrum, we have these sort of supremacy problems that kind of look like random quantum circuits. They're classically intractable, but they're essentially useless. Okay, maybe you can generate random numbers with them. But then you can think, okay, well, what's something that sort of looks like those random circuits and it's a little bit more physically relevant? And with just a bit more resources, you might be able to simulate something like scrambling in a black hole, which there's similarities between that and random circuits. Okay, that's cool. It's definitely interesting. Maybe it's also not the most commercially relevant thing. But then you can think a little bit further, okay, these devices we have, they're on a planar grid. Maybe I can do, say, dynamics of models on a planar grid, something like a Heisenberg model. And this is starting to feel a bit like material science. There are people that are interested in that. Then you can add a little more complexity. You can try to say, okay, how about electron models on a grid? And that's starting to look like a model of superconductivity. Maybe then you can add more connections, and before long, what you're simulating is something like a realistic model of a molecule. And so we're pretty certain that in the NISQ era, we're going to get somewhere on this spectrum. The question is where. Are we actually going to get to that molecule, for instance? That remains an open question. So I want to talk a little bit more about some of the other NISQ applications that you've heard about. And I want to start with a perspective that's sort of shared by the team at Google, which is that NISQ algorithms are sort of unlikely to sort of broadly revolutionize very large areas, in our opinion. It seems to us that if NISQ is really going to have some commercial value, it's probably going to apply to rather niche or rather specific problems. So optimization is an area that we've heard a lot about. Everyone has optimization problems. We have optimization problems. You have them. They're very valuable. So if you can do anything here, it's quite exciting. And it's not completely impossible, but unfortunately, in our experience, we think that optimization actually looks like a pretty unlikely use case on the NISQ processor. And the main reason for that is pretty simple. It just has to do with the number of variables required. So in order for most classical optimization problems to be really difficult, and by really difficult, I mean that a good classical heuristic can't approximate the solution very well, you need to typically have a few thousand variables. At least that's been our experience, and our team's sort of been hunting for these difficult, commercially relevant optimization problems for many years. However, it also seems like NISQ processors are probably not likely to be able to implement circuits on more than a few hundred variables, and that just comes out of a simple calculation about the error rates of the gates. So optimization looks quite challenging. Everyone is also very excited about machine learning. Machine learning on quantum data, for instance, to learn things about quantum simulation, that it requires some quantum mechanics, so that looks kind of promising. For classical data, maybe this seems like a sort of better application than optimization, but here we also don't know exactly where NISQ processors are going to help, so it's still a rather speculative application. Another one is solving systems of linear equations, which is also related to the way that people propose to solve differential equations very often on quantum computers, which is an important problem, and there is a quantum algorithm that has logarithmic runtime, which gives an exponential speedup. But the problem is that to use it, you need to be able to sort of load the equations into memory, which either requires using something like QRAM or generating those equations on the fly in the quantum computer, which looks very impractical on a NISQ processor. Cryptography, is a very popular application of quantum computers, and we do think that certifiable random numbers will have some applications in cryptography, but in terms of actually breaking encryption, that's something that it looks like far too many resources will be required for. So the other thing I just want to emphasize, and I mentioned this in one of my questions before, is that with NISQ algorithms, these are essentially all heuristics, meaning we don't really know exactly how the algorithms are going to perform until we run them. And for this reason, the value proposition in NISQ is frankly rather speculative. And in fact, there's very few papers which are able to actually estimate the resources required to do something, really anything, that's classically intractable in terms of an application on a NISQ processor. However, as a number of speakers have pointed out, that doesn't mean you don't have to prove that something will work in order for it to work. And in practice, classical heuristics are extraordinarily useful. And we do have these processors now which can exceed what you can do classically, and that certainly seems like a resource that we should be excited to try out and see if we can actually come up with use cases for it. But I think it's important to keep all of this in perspective. So I do want to say a little bit about quantum error correction, which is, there's actually been some mention of it today, which I was heartened to see. But quantum error correction, for me, it's really the dream of quantum computing. And it is also almost undeniably the future of quantum computing. So to quickly review some concepts, error correction is based in some sense on redundantly encoding information so that you can detect and correct errors. So classically, this is rather straightforward because you can just copy information, so you can have many bits encoding the same thing and just check when one is disagreeing. Quantum mechanically, you can't copy quantum information. There's a theorem about that. But there are some very beautiful ideas that are the foundation of quantum error correction that actually come from topology. And they come from the idea that topological properties are global properties of quantum states. And so if you have noise acting locally, it doesn't destroy the information if it's encoded in those topological properties. So at Google, we're quite serious about getting to quantum error correction. And some of you might find this ambitious, but we actually have a rather concrete 10-year roadmap to try to produce a useful error-corrected quantum computer. And for us, that's a device that would have about 1 million physical qubits on a planar array with the error rates we've already been able to realize in the lab. And so you might ask, what can you do with a device like this? Well, one thing that actually isn't on my slides here is you could reproduce our quantum supremacy calculation within error correction with only a few tens of thousands of qubits, which to us seems like a very achievable goal. But to do real applications, you will need more resources, and it is a large number of resources. So one of the easiest things you could do that we know of is simulating models of solid-state materials. This is something like graphene or something like this. In order to simulate an instance that would be classically intractable, requiring about 128 qubits, you would require about 300,000 physical qubits and about 2 hours of runtime. And that's with the error rates that our processors have already achieved. If we are able to lower the error rates, which we hope to, then these resources would also be decreased. You've also heard a little bit today about this particular problem of fertilizer production and about how there's this particular molecule called FOMOCO, which sort of holds the key to biological nitrogen fixation. And it's believed that if you could understand the mechanism by which FOMOCO cleaves nitrogen gas from the air, you could potentially design a better industrial process for fertilizer production and save a very large amount of energy. So this particular molecule, using the best algorithms that we know of today, you could just barely fit on one of these error-corrected processors that we're aiming to build in 10 years. It would still take about a week of runtime, but hey, that's possible. Of course, there's many other applications which will require even larger devices. So for instance, breaking 2,000-bit RSA encryption would take about 20 million physical qubits in about 8 hours. And I should mention that all of these results are based on papers that our team published earlier this year. I do want to emphasize with fault tolerance, though, that there's a huge difference between the sort of resource estimates I give for fault tolerance and what people talk about in NISQ. And that's that we can actually prove these resources are sufficient. If we can build the device, it will work, it will solve these problems in this runtime. In fact, these are actually bounds. And they're bounds that are somewhat loose, meaning that even fewer resources might be required, but this is definitely sufficient. And we also assume that algorithms are going to improve and bring these costs down. I do want to say that, quite frankly, there's quite a lot of unexplored territory here in terms of figuring out the resources required for fault-tolerant applications. Unfortunately, there's not a lot of industry groups which have really published work on fault-tolerant applications, and so there's very little work on areas like optimization, linear algebra, and machine learning. I should say a couple companies have been working on this, but it's generally a lot less popular than NISQ development. So to kind of drive home the point about how important it is to be doing this development on error-corrected algorithms, I wanted to show this table here. What this table is it's a list of the historically best error-corrected algorithms for solving the quantum chemistry problem. And I'm showing the main thing to look at is the right two columns. So the asymptotic number of gates required, or the scaling of the method, and the actual gate count where people have bothered to compile an instance all the way down to a concrete gate set. So maybe we'll just draw attention to these two results, which give you some sense of how things have improved in the last 6 or 7 years. So Microsoft was the first to really take this seriously and ask the question of, okay, let's actually figure out how many resources we need in fault tolerance to solve a problem. And they took it, what at the time were state-of-the-art algorithms for quantum chemistry that no one knew how to improve on, and they estimated something like 10 to the 18 gates would be required, which was quite a large amount of gates with an algorithm running like n to the 9. But since then, people said, okay, here's something concrete. We can really try to improve these numbers, and everyone took a little chunk of it and tried to improve it. And today, we're looking at algorithms that are scaling closer to n to the 2.5 with only about 10 to the 7 gates. So that's an 11 order of magnitude improvement, not too shabby. And I believe that these costs may still decrease. So it's very important for us to be doing this work. Having said that, the road to error correction, it's long. It's going to be challenging. It's full of both RISC and NISC devices. And what I mean by that it's full of NISC devices, is just sort of rhetorically the devices we have before error correction are going to be NISC devices. So while it's critical to figure out where this road is headed, what we can do with a fault-tolerant device, it's also important to figure out what can we do with the devices we have in the meantime. And there is a real risk in sort of running out of goodwill and funding in the field if we aren't able to find anything in the meantime. So it's a very important goal. So that kind of concludes the part of my talk where I wanted to give a more general perspective on the field. And the rest of this talk, I'm going to discuss sort of Google's vision for working with customers. So I want to start by saying we are productionizing the hardware that we achieve quantum supremacy on. In fact, my team, which is the algorithms team at Google, has spent the last 4 months or so running a number of application experiments through this cloud interface on the hardware. However, having said that, time on these devices it's a scarce resource, and it's going to remain a scarce resource, certainly through the rest of next year. So we have to think about how we want to spend that time. And our objective at Google is to use that time in order to facilitate scientific progress. Specifically, at this point, we're not interested in revenue generation, we're not interested in market position, and we're certainly not interested in overhyping experiments. We're interested in actually figuring out what these devices might be good for. And along those lines, we're looking for commercial partners to work with us on application development. In particular, we don't want a huge group of customers. We're looking for only a couple customers who could work with us in each industry where we think that there might be an interesting application. And the goal here is really to work with domain scientists who may be using quantum computing and to be exposed to what those applications really are. So Google is, of course, an internet company, and we have our own applications in areas like machine learning and cryptography, and we're first and foremost our own customer. So we are, working internally. But we also are currently already working with customers in automotive and energy and materials. I'm not going to say that we wouldn't necessarily take new customers in those areas, especially in materials, which is particularly tantalizing. But at this point in time, we're especially focused on working with customers in areas where we don't currently have customers. This isn't an exhaustive list, but chemicals, pharmaceuticals, finance, electronics, aerospace are areas that we'd really like to develop some partnerships around. And our idea here is that if we're able to help just one customer find one application that's really valuable for their business, we can focus on that and we can help develop that into a real solution for them. And of course, this customer may realize some sort of first mover advantage and sort of be rewarded for working on this first. But once we figured out how that solution works for that customer, we can work on scaling that solution to others in the industry. So the idea is let's just find an application, and then we'll worry about sort of growing the business later. That's our mentality anyways. So the focus is really technical progress right now, and we want to do that in collaborations with customers. We are not a consulting business at this point in time. So I want to say a bit more about what it's like to collaborate with Google. Ideally, we'd like customers to feel like they're essentially treated as an extension of our research team. So especially on the topic of application research, we do sort of our flagship research with our core researchers at Google with customers, and we include them in those publications and also in those experiments. So at this point in time, we're not in the business of sort of just giving people or selling time on our device per se, but customers are actually already running experiments with us. But the idea is that we sort of design those experiments jointly. So we understand the customer's applications, we talk about their objectives, and then we also try to design an experiment which advances our own research interests at the same time and work together on that and try to actually push the state of the art in the field. But for that to really work, customers actually have to have their own scientific team, and it needs to be a strong scientific team. And beyond that, we need to have a certain compatibility in perspectives. In particular, we need to have customers who are excited and are willing to embrace the idea that what we're doing, while it's research on applications, it is fundamental research, essentially. And furthermore, Google thinks it's important at this point in time to be publishing this research openly. And while we're happy for customers to develop their own software and their own IP and to use proprietary software, when it comes to tools that we're actually developing jointly and Google's helping to develop, we would like for that software and those algorithms to actually be open source. We think that's important for the field. And finally, we want to see a long-term perspective here and sort of a serious commitment to the idea that this is research. So at the moment, we are only signing contracts with customers that are 3+ years. And ideally, we'd actually like to see customers who will work with us on finding NISC applications, but if that doesn't pan out, if we can't find NISC applications, we want those customers to work with us until we have error correction. And that's what we would really like to see. So you might be asking, where do some of the quantum software startups that we've heard of today, like a Zapata or QC Ware or something like that, fit into this vision? Well, in some cases, we already have customers who are collaborating with us who have actually hired third-party companies like this into a collaboration with us. Maybe they want to use the software from that company. Maybe they just want additional consulting for educational purposes, or maybe they just want them to help with the research. So we're totally happy with that. In the future, there's also other modalities, other ways that we would like to work with these startups, but at this point in time, that's sort of the most straightforward. So it's one thing to sort of hear from me what it's like for Google to work with customers, but I thought it would actually be a good idea to invite one of our actual customers onto the stage for a few minutes and hear from him a little bit what it's like to work with us. So I'm going to invite up Tyler Teixeira from the Daimler Quantum Computing Group. Here you go, Ty.
Thank you. Hello, everybody. I'm very excited to be here today to tell you about this, because this is a unique opportunity for me. Normally, when I'm up here on stage, I have to tell everybody about what it is that Daimler is doing in quantum computing and why is it we're doing it. But today, I also get to tell you about something that's actually a really big challenge for industry, and that is how you work with your industry partners in order to accomplish your goals. So at Daimler, we have really localized at the moment on 3 major areas where we're interested to understand whether or not quantum computing has a role to play. And like Ryan said, we're not sure, right? And so we want to understand, well, we want to explore with our partners when and where this would become valuable, or if it will at all. And so one area is mobility solutions and optimization. The other, obviously, machine learning. And the third, chemistry and materials. And the approach that we're taking is collaborative and fundamental research that is motivated by realistic use cases within our industry, right? And the reason we're taking this, like Google, we believe that in order to understand where it is the technology is at the moment and its limitations, you have to do research so that you can be on the cutting edge. And that, we believe, will give us the skills and core competency that eventually will allow us to follow and track this technology as it develops, right? And so at this point, I'd just like to give you a quick idea of how it is that we work with Google and tell you about one of the recent projects we've done in the area of chemistry and materials. And so this is a collaborative research project where we developed a quantum algorithm. Now, Daimler is interested in chemistry and material simulations because we'd like to understand whether or not it is possible for us to efficiently produce or design materials computationally. And so when you sit down and look into the field of quantum computing, you realize that in order to perform accurate chemical simulations, it actually requires an enormous number of quantum resources, right? And so for an example here, I've plotted just a little plot here where I've taken a chain, an atom, a hydrocarbon chain, and I've systematically added black balls to it. Those are carbons. And you see that if you want an accurate chemical simulation, by the time that chain has 8 carbon atoms, you require over 2,000 qubits. And so this is the type of fundamental research in question that is motivated by a use case within Daimler, but that's something a partner like Google would be very much interested in. And so what we did is we designed a team. We took experts in chemistry and materials from Daimler, and we paired them with chemistry, physics, and quantum computing experts within Google. And together we designed an algorithm to address this problem, or at least make some steps along this road, right? And I'd like to share with you some of the results here. So what's important in this plot is that there's a bottom curve, and you've seen curves like this before. It's the potential for pulling 2 atoms apart. And the bottom curve is a 20-qubit calculation, which is fairly accurate. But in reality, most people and most devices require you to use a very limited number of quantum resources, and so that blue curve at the top is a 4-qubit calculation, and you can see that they're very different. But the results of our algorithm are the red dots on top of the green line at the bottom, which only required 4. And so these are the types of things we're interested in, right? Finding a problem within industry, making sure, boiling it down to a fundamental problem within the field, forming a team, and then coming up with some contribution back to the scientific community. And we continue to work and collaborate with Google, not only on quantum algorithms, but also experiments. And this is just one example of how we worked with Google, but as Brian mentioned, recently they've performed a supremacy experiment. And what you may not know, and what we're going to tell you a little bit about, or Ryan will tell you more about in a little bit, is that in parallel, Daimler was working with Google on an experiment on the Sycamore chip related to the field of chemistry. And so I'll hand it over to Ryan right now, and he'll tell you a little bit more about this, and we're very excited.
Thank you, Jai. I should also say this work that we did with Daimler was just accepted in PRX, too. Okay, so yeah, as Ty mentioned, we actually been working on an experiment together as well. And so we've been working on this since the summer. As a scientist, I couldn't give a talk without sharing a little bit of data. So I don't really have time to get into the details of this whole story of how we do quantum chemistry on a quantum computer. I'm sorry if you don't know what these curves are. But for those that do study the subject, this is a molecular binding curve. And these are actually results on a calculation from our Sycamore processor. And I know what you're thinking. You see the x-axis here, which says HH distance, and you're thinking, oh my God, did they do yet another molecular hydrogen calculation? Not exactly. This is not H2. This is H12. And that's a result that we're pretty excited about, because this is more than double the number of qubits and number of electrons as the largest prior chemistry experiment performed on a quantum computer. There's more than 10 times the number of gates. And despite that, it has achieved a level of accuracy as prior results. However, it is kind of boring to just do these dissociation curves. So this next plot, I should say, is not experimental data. It's simulated data. But we are also working and hope to publish both of these results in the next couple months. The sort of elucidation of a chemical reaction mechanism, specifically the isomerization of diazine, and we want to use the quantum computer to actually distinguish between two competing transition states. So stay tuned for that. We're excited to be publishing that with Daimler. And I didn't have much time to talk about Google's open source philosophy and the software frameworks that we've been developing, but to do this experiment, we used our platform for performing quantum chemistry calculations on a quantum computer, which is called OpenFermion. You can find it at openfermion.org, which works, which is compatible with Google's API for composing and compiling quantum circuits, which is called Circ. And we actually used Circ to directly control the quantum hardware in this case, which was our Sycamore processor. So with that, I want to essentially conclude the talk. This is my final slide, and I'm just going to sort of recap the things I've said before. So NISQ it's rather speculative that there's real business value there, and if there is value, it's probably fairly niche. However, it's also promising. It's something that we should be excited about, but we should also be taking quantum error correction seriously. It is the future, it is the dream, and we will be there eventually. And it's probably the modality of quantum computing that will have the greatest overall impact on business. Having said that, this hardware that's capable of quantum supremacy, it allows us to test new NISQ heuristics, which is a powerful resource, and we should keep trying to do that. We're going to have these devices on the road to quantum error correction, so we might as well use them. Google is productionizing its hardware. We will have a cloud service, but the resources on that on those devices will be limited, especially through the next year. And our priority is to use those resources to help facilitate application discovery on quantum computers. And in particular, we want to do this with a select group of customers that have a research mindset. So if you're interested in learning more about working with Google, if you think you might be interested in partnering with us, I highly encourage you to reach out. Anyone who has logo like this on their shirt. It's a 1 inside a 0 because it's in superposition. That's our team logo. So you can find someone with this shirt, or if you're in the United States, you can reach out to Harach. If you're in Europe, you can reach out to Marcus. They'll be fielding inquiries from potential customers, and you can of course find me and talk to me anytime during this conference. And with that, I would like to conclude and see if there's any questions. Thank you. Oh.
Well, thank you very much for your talk. Could be a quick question, could be a very elaborate question. The customers that you're interested in, are they only the industry customers, companies, or are you interested in working with academia as well?
Oh, we're very interested in working with academia. So Google has many collaborations with universities. We give quite a large amount of money to academic collaborators every year. And we will also be prioritizing high-impact academic experiments as some of the first users of our cloud platform. So that's not officially announced, but there will be more details on that at the appropriate time.
Fantastic. Thank you very much.
So as we all know, VQE takes a lot of measurements to estimate expectation values. Can you comment on some of the work your group is doing to reduce the number of measurements and allow for faster convergence of VQE?
Sure, yeah. So you're asking about the topic of measuring the energy in VQE. So yeah, that's something our team's done a lot of work on. We've published a couple papers that have reduced the amount of resources required for the chemistry application by a couple orders of magnitude. I believe actually Bill Huggins, who's a PhD student at Berkeley and was our intern doing some of this work with us, will speak about that in one of the sessions on Thursday. So I think you can go to his talk to hear more. Oh, I get 3 questions.
Hey, Ryan.
Hey.
Very nice talk. So question, how should we think about evaluating the efficacy of these heuristics that we'll be building with our more powerful quantum information processors?
It's a very good question. I mean, that's one of the main research questions that we face right now. So on one hand, there's the philosophy that you just try it out and see how it does, and then you try to compare it to the best classical heuristics you have available, and you see what does better. Of course, you can also do studies where you attempt to infer the scaling by, doing the same thing at smaller problem sizes and drawing a line. Beyond this, I'm not sure there is a whole lot more you can do. But I mean, one thing you can certainly do is you can work on compiling the primitives that are repeated to execute the heuristic, and you can work on reducing the resources required for that. And our team's been working on that as well.
So in terms of your efforts towards quantum error correction codes and so forth, are you looking at physical systems beyond just superconducting circuits, as well as what types of error models you're considering in that?
So Google keeps its eye on a number of hardware platforms. We're always worried there could be some disruption, but at this point in time, we're confident in our approach on superconducting qubits, and that is the sole focus of our hardware team. In terms of the error models that we're considering with the error correction schemes that we're pursuing, generally the idea is that they're local error models, and these are error models that we've actually been working to validate through experiments on our existing platforms, and so far we see agreement with those models.
So in terms of industry collaboration, how do you think Google differentiates itself from the competitors like IBM, Amazon, and the others?
Great question. Well, I wish I knew with Amazon. They're sort of new to the game. I mean, I don't know if I want to comment on how others work with customers, but I would just say that our priority is working with a relatively small group of customers in very close scientific collaboration. So we really don't think of it as anything approaching a consulting service. We think of it as we're partners that are collaborating together. And I mean, you heard about some of the other perspectives today, so you can sort of decide for yourself, but I think that's a little bit of a different perspective than some of the other groups.